today we are going to talk about classification, and we have two different lectures for classification. The first one will cover the classical approaches, which were there before deep learning. And then we will talk about how classification can be solved using deep learning approaches. Okay, so we have two different lectures for the same topic. And this is the first lecture. The outline for this lecture will be, first we will briefly cover the basics of classification, and most of that we have already covered in this course in previous lectures. And then we will move on to like different kind of classification approaches which were there before deep learning era. And we will start with nearest neighbor classifier. Then we'll talk about maximum margin classifier. And finally, we'll talk about support vector machines. Okay, so let's start with the first segment, which is just covering the basics of classification. And as I said, we have covered most of it like in the previous lectures. So I will quickly run through these slides. And if you have any questions, you can later ask those questions. Okay, so the main idea of classification is, given a sample, you want to actually identify which class category this sample belongs to. And in that, you will have like some set of classes. Okay, so you'll have to choose one and say, okay, this sample belongs to this particular category. And one simple example for this could be like your, let's say, digit classification. You could have your data set where you have images of those digits, and digits will be from 0 to 9. And a simple classification problem will be given an image of the digit. You will say like which of these digits is present in that image. Okay. Now that will require, because we have like we have numbers from 0 to 9. So that will require like a 10-way classifier, because each sample could belong to either 10 of the either one of those 10 categories, right? So before moving on to like multi-label, that's called multi-label classification or multi-class classification. And that's like a more advanced scenario. But let's begin with like a very simple case, which is called binary classification. And in this case, the idea is you just have two classes, or even like a simpler case, you might have just one class. And the idea will be, for example, if the class is person detection, so you have to detect whether a person is present in an image or not. So you can solve that as either person is present, that will be one class. Person is not present, that could be the second class. All right. So the way it will look is now we know features, and features we know like it has like a certain dimensionality. For example, it could have like, let's say 10 different numbers, or it may have 1,000 different numbers. Okay, so that will be your features. And in this case, I'm just showing you features which are two-dimensional. Okay, so this is your Euclidean space. And all these dots over here are your samples. All right. And depending upon what's the X and Y coordinate, or you can say like those two are your features, where they lie in the Cartesian coordinate or your Euclidean space, you are just putting that point on that space. Okay. So in this case, the blue dots are, let's say, category number 1, and the orange dots are category number 2. And here you can see that you can actually draw a very clear straight line between these two categories. And if you remember, like from your algebra or maybe numerical analysis, like your high school maths, you know that you can represent a line using a simple equation. And if you have that equation for this line, that equation can serve as a classifier. And then you can put like each of these points in that equation of line, and depending upon what's the sign of that of the resultant value, you can estimate whether that point is actually towards the blue side or towards the orange side. And if the point is exactly on this line, then you will get perfect 0. Okay, so over this line, all points are perfect 0, and it could be like all the points towards blue are negative and all the points toward orange are positive. Okay, so in this case, this line, or you can say like a simple equation, is serving as a classifier. Right, so you can have like different categories of classification problems. As I said, you can have digit classification. So for that, we have MNIST dataset, and this is roughly like 60,000 images, and the images look something like this. So each image is corresponding to one of the digit. Right? And the classification task is given each of this image. You have to say which digit is present. And then again, we have a multi-MNIST. In that case, I don't have the samples, but it will look something like this, but you will have multiple digits on same image. Okay. And then again, we have this SVHN data set. Again, this is also digit classification. And these are, you will say like more realistic images, because these were extracted from this HN represent like house numbers. Okay, so these were extracted from real house numbers, and you can assume that they will be very noisy. And again, but each of those images are actually corresponding to one of these digits, not as clean as this. Then we can have object classification. Again, we have several data sets here. We have CIFAR 10. It's called 10 because there are 10 different classes. Then we have extended version of that, which is CIFAR 100, where we have 100 different object classes. And then, of course, we have ImageNet, where we have billion of images. And again, there are different subsets of this. This standard one is like 1,000 classes. So if you have to solve the classification problem on this data set, it will be 1,000 classifier. All right, so again, classification, you can call that object recognition as well if you're interested in some set of object categories. And as we discussed earlier, a simple variation could be binary classification, where if you're interested in persons, the question will be whether person is present in the images or not. And your classifier should provide you this answer, either yes or no. Okay, so ImageNet, I think this is the most popular data set for image classification, and we have roughly 1,000 categories, as we discussed earlier. We have 14 million images, and I think this is growing daily. They are increasing the size. They're collecting more images, and we have roughly 100K testing samples here. So this is like a huge data set. Just training like simple architectures on this model, if you don't have enough GPU resources, it takes actually weeks. And in that sense, it's challenging as well. Okay, so those were the data sets. Now you understand the high-level idea of classification. Now the overall approach you take when you solve any classification problem is, given a training images, you have to separate those images into validation and testing. And again, we have covered these things before as well. So I'm going to quickly go over these. Okay, so the idea is validation. Images are something, when you train your model on these training images, you evaluate on these images, and depending upon whether your model is performing well or not, you can try to you can try to fine-tune your hyperparameters, right? For example, if you want to increase your learning rate, decrease the learning rate, or you want to change the number of layers in your model, if you want to use like more kernels. So all those hyperparameters you can change depending upon how your model is actually performing on this validation set. And testing images, again, you don't have like labels to these. They will be only used for evaluation. And you don't use like feedback on this test set to actually improve your model. Okay. So the learning phase will be, you will have your training images, you will extract features, and then you will train your classifier over here. And to train that, you know that you need the ground truth labels. In this case, classification, you will only need which object is actually present in your training samples. And that will give you like the training signal, which for which you can have a loss function. Okay. And at the end of this, you will get a train classifier, which you will run on your testing images. And again, for testing images, you will use the same feature extraction steps, and you will use the training model to make the final prediction. And of course, you will have labels for these testing samples, and you can evaluate how good your model is doing. So that's like overall training process, which you have to take. Now, let's quickly go over these features as well, what kind of features you can use. We can have raw pixel values. We can use directly those. We can use histograms, for example, HOG features or SIF features. We can have templates. And there are a lot of like other set of local features which are actually very useful for classification. And eventually we'll have, so this is something like which we will focus on this lecture. And we'll not specifically talk about these features because we have already covered like how we have to extract HOG and SIF features, right? Those are some of the variations. But what we will cover is how to use those features to solve the classification problem, because this is just the first step, right? And later on, we will see like, what if we don't want to use those extracted features? What if we want to learn those features? So in that case, that's the second part of this lecture where we'll talk about how without extracting these features, we directly train your model end to end by directly operating on your input images. Okay, so whatever approach you do, the general framework is always kind of a function where input is an image, where either you can just pass your image to your model, or you can extract features and pass those features to your model. And that model is going to make predictions about your images. Okay, so basically you have this function, which you can say a prediction function or a classifier. You'll have image features or the image itself, and y will be your output label. And again, you can, depending upon which method you're using, but this overall framework is never going to change. Okay, it still remains the same for whatever approach you use. Okay, so binary classification, as we said, you have to, given a sample, you have to just assign like one of the classes to it, because you only have two classes. And most of the time, binary classification is used when you want to say something is present or something is not present. All right, so again, these are your set of samples. This is like one category. You can say this is positive category, or this could be your negative category. And your classifier will look something like this line. We discussed this briefly earlier as well. So this is the simple case of binary classification. But what if you have multiple classes? Let's say you have crosses, then you have triangles, and then squares as well. So in that case, you can see that this simple linear line is not going to help, because you can't draw like a line to separate three different classes. Okay, so one simple solution could be you actually learn three different equations. And if you draw something like this, which is separating like these classes from one another, then your classifier is actually consisting of these three lines. Okay, so if you think about this, one simple way to solve this is, when you're learning this red line, so that could be your one classifier, and of course you can learn that function. What you could do is you can treat these crosses as the positive class, and then you can treat the green triangles and the blue squares as a negative class. So you don't distinguish between green and blue. You treat these as one classes. And then you can train like a binary classifier, which is the red line. And once that is trained, then that red line can actually tell you whether the red crosses are present or not. You don't care about like what are the other classes. You only care about red crosses. Okay, so that's like one linear classifier for you. Similarly, you can do the same thing for green triangles, right? And for that, let's say you learn like a linear line. And that line will learn whether green triangles are present or not. If present, you have these green triangles here. If not, you don't care whether it's like a blue square or a red cross. And similarly, you can do for the blue squares as well. So basically, if you have three classes, the simple approach you can take is you train three different binary classifiers. And you can use those to actually do multi-class classification. And that usually works like pretty well in most of the cases.